The title of my presentation, the genealogy and the fingerprints of digital twin. I will start the presentation with a video. That's lowering the audio. I think most of us are familiar with this kind of digital twin or these softwares that bring to us the digital twin to manage some machine or equipment. I think it's okay for now. So this kind of technology is already being used in some industry sectors and mainly for management. I think there is many companies doing this kind of stuff. But right now we are interested in bringing this concept or technology for our own sector, the construction sector. So in this class, I would like to propose those ideas in that order. I would like to postpone a formal definition of digital twin. Most of you know that is not a consensus in our scientific community about what exactly is a digital twin. So I want to contribute a little bit with my own view of this subject. And I want to bring this, what I call the genealogy, because we need to understand what came before the digital twin or this technology and what contributed to this moment in time when we have a lot of different technologies that could be brought together and make the digital twin this new technology. And we need to also understand what are the components. I think the digital twin is a system, and this system could be subsystems and components. And I'm calling this the fingerprints of digital twin. We would elaborate more in the middle of this class. And in the end, I would like to finalize my lecture proposing a framework so we could at least design or specify the components of our digital twins and could develop ourselves or hire people to develop it for us. I proposed 2 articles for the audience to read it before my lecture. And one of those articles is this one from Tao. I brought some of his questions. He proposed 5 research questions in his article. But I only want to talk about 2 of those questions. In this article and in many others, it's clear to all the community that there is different understandings about digital twins. And one way to see digital twins is to focus on the simulation part, is what digital twin do. The other part of the community want to see the digital twin as what are the components. So they specify or understand digital twin based on those components and don't look at what it does, but at what it contains. So they look, oh, there is a physical part, there is a virtual part, and there is a connection between those parts. But they don't talk about what it should do. So I hope in the end that the audience could understand better what is a digital twin and how to implement it after my class. I also pick up 3 different definitions that the article Tao et al. Proposed, and I pick up the words and transformed those words in these 3 diagrams because it's not useful. We just cite a lot of different definitions because authors choose different words for the same concept. It not helps people that are trying to understand what is a digital twin. So I draw these diagrams, hoping to create a better understand of 3 definitions that I like them. My view is really towards that definition that look at the digital twin based on what it should do. And I highlighted what words or concepts are similar. In red, I try to highlight the part that represents the digital twin itself, that is based on the state of what we are twinning. Então, I think some authors say the word state, but the first one said accurate simulation in different scales of time and space. But it represents the state that is different in time, that is different in space, but it's the state itself. And in the third definition, the authors just say the digital representation. But the digital twin is that it's a digital representation, the state, the actual state of it. But also I highlighted other parts that explicitly said about the simulation. Again, I'm choosing those definitions because they talk about the simulation, but there is many others that don't talk about it. And look, there is the classification or qualification of the simulation. It's clear for us that we need a better simulation, a more modern multi-physics, multi-scale, probabilistic, ultra fidelity, or spatial simulation, because the digital twin is a step ahead of what we have been doing simulation from the many decades before our current time. And also, that is the part, that is the data that comes from the physical environment to the digital environment. And mainly there is 2 types of data. There is this, one author said expert knowledge, the other one physical model, but in reality it's almost the same thing. And that is our ability to mathematically model our physical assets. But there is also another kind of data that comes from the real to the virtual world. And one author writes the real data collected, just real data, and the other one calls historical data. It means the past data we acquired, probably by sensors, and that is the real-time sensor data. The real-time sensor data, when it's accumulated in time, it becomes the historical data. So this is a tentative to show similarities between definitions, even if the words are different. And I could have put many others in this diagram. But looking at the digital twin, we must understand the context that made it possible. And one way to look at it is understanding the context of the fourth industrial revolution, I 4.0, and looking that it contains a lot of different new technologies, and following the 9 technological pillars proposed by the Boston Consulting Group in these technical reports. We could look at autonomous robots, simulation, system integration, industrial IoT, cybersecurity, the cloud, additive manufacturing, augmented reality, big data, and analytics. And somehow there is not explicitly the digital twin, because the digital twin is a combination of those pillars. Each one, I like that proposition. I think each of those technologies represent different dimensions of possibilities, and the digital twin is a combination of simulations, a combination of industrial Internet of Things, of big data and analytics, and so on. So this is the context. I will not elaborate more because we could talk a lot about those things, but I think most of you know a little bit about these things, but we need to have it in perspective. What I need to bring now, and this is the part we begin the genealogy of the digital twin, is understand that I think all authors agree that Dr. Greaves in 2002, 2003, in his course on PLM, product lifecycle management, he conceived the idea of the digital twin, although he did not call that idea digital twin. The terminology was only proposed 10 years later. But it's really in this context of model-based systems engineering that this idea was conceived. Because there was a transition between doing project or doing design in a document-based approach to a model-based approach. And Dr. Greaves was talking about, okay, we now have a digital model. We could make a lot of things inside the computer using this model. We could simulate and test a lot of engineering performance of this future physical asset in the computer instead of doing it in a physical prototype. It's better to and is less expensive to do this experimentation in bits instead of atoms. So this is the beginning of the idea. And talking about this model-based system engineering, we also have the PLM itself, but most of us know more the BIM, the Building Information Modeling, that is somehow similar to PLM, that is more used, this terminology is more used for the manufacturing sector. And from the other article that I propose a previous reading, I bring many characteristics of the digital twin that makes it different from PLM and BIM. digital twin is really an evolution of this concept, but it brings many different things. It is really much more than PLM and BIM. So we need to recognize it. And I highlighted some words here. Digital twins, a really specific instance, and it has mission specific characteristics. It's used mostly to preventive maintenance, and it captures the behavior, not only the geometry of the asset. We use it to have some expectation in how it would perform in the future. We have a way to observe the behavior of the object, and we could experiment in the computer, get a better understanding of the operational environment. There is this connectivity between physical and virtual world. There is this digital thread. We could make predictions about future system performance. We could troubleshoot if our twin is a equipment. We could troubleshoot malfunctioning, remote equipment. We could perform remote maintenance. We could optimize services and manufacturing process. If you are twinning a factory, or if you are twinning an activity on the construction site, and so on. So this is some characteristics that leads us to understand the digital twin are dynamic. It is not static as PLM and BIM. And even if this kind of dynamic it's obvious that I could update a BIM model, but the kind of update that is made throughout the life cycle of the building, for instance, is very different for the constant update and most of the time automatic update made by sensor data that is possible with digital twins. And we need to acknowledge that digital twins, as it needs the physical twin to work, it is best for management, operation, and maintenance. I would also to brought, besides this model-based system engineering, the simulation as an area that has been developing throughout the past decades. And maybe the digital twin could be the next wave in simulation. We could see three past developments in simulation or evolution, beginning with the simulation of specific devices based on special tools, and then we could do simulation of generic devices on standard tools. And right now we are in this being able to do simulation multi-level, multi-scale, and multidisciplinary. Many people don't recognize the difficulty in doing multidisciplinary or multi-physics simulation. Most of the time you do, for one particular equation, you do the simulation, pick up the result, and eliminate the other part of the problem. And if you look at, for instance, a car, a vehicle, that is, or an aeroplane, there is many different physics that happens with it, but it's really difficult to look at all those physics working together. We can't make it easily a simulation considering all this kind of information. But right now we are developing this kind of things. And maybe the digital twin could provide us with real-time simulation throughout the product lifecycle. And in the as a particular view is really what I'm looking as a research challenge for me, is trying to use these neural networks as the core of the simulation. I think in the past 5 years, this kind of thing started to be brought by some authors, and it could substitute the way we do simulation. So we could use part of the physical equations that we know our asset is based, its behavior is based in some mathematical and physical equations. From one part of these possibilities in the spectrum of how it should work. But in the other one, we could use a lot of data collected by sensors. And in those data, indirectly, we could understand also the way our system is functioning. And using these PIMs, these physics-informed neural networks, we could bring together the best of two worlds using equations. It's a kind of limitation in the space of solutions, but also we could use a lot of data that contains the specificities and uncertainties of the real world. So combining those things, I think it could provide a strong simulation. It could be the base for our digital twin. And another theoretical content that is important for digital twin is this data simulation. It's based on probabilistic theory used in other fields, but also important for ours. And in this graph, I understand that is not really clear, but somehow it is showing to us that our model, this green part, we have some uncertainties represented in these ellipses, and we have the truth about the state of our asset in blue. Look, that is, this circle is the same time throughout all, the same size throughout time, but the uncertainty of our forecast based in our model, as we get data from the real asset, and we are calculating or providing an analysis, this green uncertainty, this red uncertainty about what is our prediction of the behavior of this asset is getting smaller. So we have more certainty that we are getting at the true value of the real estate. So it's really based in a solid mathematical foundation, and also think this is a really important theory that we should be studying and using for the digital twin. And we have also to acknowledge that the cybernetics area is really important to understand the digital twin. The cybernetic is the science of communication and automatic control systems for both machines and living things. Look, that cybernetics is the base for a lot of other technologies, control theory, information theory, artificial intelligence, optimization, operations research. So it's good. So we could look a little bit inside it. But the part of it that is important to us is the control and system dynamics. as I am a mechatronic engineer, I have this background. For my undergraduation, we have many disciplines talking about it, and somehow the equations that we use to model the behavior of our system, the behavior or dynamics is different words for the same concept. So that is really a theory that allows us to create this mathematical model. And this mathematical model allows us to look at the evolution of the system through time and based on interferences of the real world in the behavior and how the behavior adapts to this kind of perturbation. The digital twin, when you want to control some equipment, it would be as we were proposing a control for a system dynamics. And to end this this genealogy part, I would like to bring two examples to areas that have similarities with what the digital twin actually should do. That is this structural health monitoring system. Although they don't use real-time data to make analysis of the structural integrity of buildings, of bridges, other assets. I think they have a lot of experience, and there is a solid theory behind it that could be useful for us. And also there is these BMS or building management systems that is mainly responsible for the automation of commercial buildings. So that is really softwares and hardwares to make these things. The evolution of the structural management health systems and these BMSs would pass for the way of the digital twin. So bringing all these fields together and proposing a genealogy of the digital twin, I draw this other diagram and trying to provide in which parts of the digital twin each one of those areas could contribute. And look, that is I'm really putting the digital twin, the difference from BIM and how this control and system dynamics part could be important for the predictive output, and the technology and hardware and software from BMS and SHM could also help us to develop better digital twins. So this is the first part. The second part, when we are trying to look the components or the fingerprints of digital twin, I think it's important to reduce the scope at what we are talking about and understand that those technologies from Industry 4.0 could provide many different scenarios where they could be used or used for. And I want to look exclusively in the scenario of a support system. It would be a human-centric support system, and it will provide for us a data-driven decision-making. So the people would receive the support of this technology to make a better decision or a better work. This kind of scenario is also known as operator 4.0 because of the 4.0 revolution, or is known as the augmented worker. And I think this is an interesting scenario because those technologies, if it is applied to industrialized construction or modular and offsite construction, it could draw inspiration directly from the manufacturing sector. But when we try to bring it to the construction site, we need to look at those technologies differently. And I think looking at these technologies as supportive system help us to make a better design decision, not only for the digital twin, but for other technologies. Looking at the fingerprints, I also brought two models about the digital twin. This is only two. There is many others that instead of looking at the components or parts, it looks at the different layers. But I think if you will look to this with 3 dimensions, the physical space, virtual space, and the connection, or if we look in detail in each of those 3 parts, we could explode it and it becomes 5 parts. I think it's okay. It's a way to see it, but maybe it don't help us to go forward and understand exactly what is a digital twin or how we could implement one. But it helps us to have some or concentrate in the main ideas and the frontiers of what is a digital twin. And I always want to highlight that a digital twin is digital. It is software in the end. It uses data from hardware or real equipment or the real environment, real world. But in the end, what we are implementing is digital. And as I said before, in my view, the simulation is the core of the digital twin because I'm looking at what it could do. And from these connections and interactions between the physical and digital space, we could look, it's like a feedback loop. Feedback loop is a terminology of those control systems. So we could control or steer the system if we pick up information where I am, what is happening right now. Okay, this is happening. I reasoning about it. I made an analysis and provide a command to put the system in a reference that we are following. We could think about a vehicle in the highway. We want to drive it straight, but if I see a danger in my front, I look at it. I decide I need to avoid it. I need to change direction for my left, and I actuate I give information for my car to turn left, and then I avoid the obstacle, and then I need to go back to my straight line, and then I turn right and follow straight. So this is our feedback of information. We look with our sensors from information of the real environment. We make analysis, and we decide what we should do, and then we bring the system back to our task that in this example was follow a line. When we look for the data flux, data is the real environment to our virtual world, we could understand that it's like a IoT subsystem. So it's a technology that is integrated in our digital twin. And if you look at the other part of this connection from the virtual to the real world, we could also look at the cyber physical system, because the cyber physical has a physical part. The digital twin is only digital, but the cyber physical has a physical part. So the software part of a cyber physical system could be a digital twin. And we could also, looking for the fingerprints, understand the uses of digital twin. This is a virtual representation. Using this software is easier to manipulate and study our system, the system we are twinning. And in the software could be this test bed environment, so we could explore it. It is flexible, it is cost effective, it represents the behavior and sensitivities, but for it to be true, it needs to be really one step ahead of our current simulations. And secondly, all this data produced, but from our digital twin, could be used as a tool, so we could explore what if scenarios, what if conditions. And based on that exploration, we could provide better designs, optimize maintenance cycles, and have ideas for new systems, and so on. Also, looking at the fingerprints, we should be aware of standards that was already published, and that is an ISO for digital twin. It is based in the IoT preview standards, and we could look at the definition for the standards, a fit for purpose. Each digital twin should be developed based on different purpose. It's rarely it could be all things you could do with those physical assets. Probably you need to develop 2 or 3 different digital twins, one for each purpose. But it's a fit for purpose digital representation of one observable manufacturing element that is our physical asset, with synchronization, that is this connection between virtual and physical environment, between the OME and its digital representation. And this OME could be a personnel, equipment, material, process, facility, environment, product, or supporting document. So it's really have a large scope of definition, and it's based on a position paper, this digital twin definition and value, that I bring to us in this next slide. Following the definition of this paper, the digital twin is a set of virtual information constructs. We could understand it as a set of different models. We could understand it as the geometric model, as the dynamic model, and so on. And this set of virtual information constructs mimics the structure, context, and behavior of an individual or unique physical asset, or a group of physical assets, and it is dynamically updated with data from its physical twin throughout its life cycle, and informs decision, is what the digital twin does, that realize value. I also like this definition. And inside the standard, we have this framework is another possibility at looking at the components of a digital twin. And also there is this article. I could in the end pass the reference completely for you, but I think it's really interesting. It uses many ideas that I put in the genealogy, and it brought to us this digital twin of a bridge that uses the pin for to interpret the sensors and look at the structural health of the bridge. And there is this probabilistic graphical model that data simulation components that made it possible to combine all kinds of information that you have about your physical asset. It could be report, it could be the expert knowledge, data from sensors, and based on that, we could provide better maintenance. And it's really a live digital twin. So this is really, I think, the components that I want to see in a digital twin. So the last part of this class is when, based on all that I talked about, I want to propose a framework, and I design it a little bit different from what we are, some of people from JetTech is know before. But I design it so I try to make clear there is also this virtual and physical space, the physical twin, the digital twin, and we should look at these functions F and G because F is always receiving different types of data, but the output of those functions should always be the same. It always should update the status of our digital twin. And also the different applications of our digital twin would be the different Gs that we could propose. And if we look at these functions, if we understand what we need to do, it will help us to specify or develop ourselves or implement our digital twins. So our Fs, the important part is that inside this function, it could be a pipeline when we could do a lot of calculations, and it is designed so we could, for instance, bring RFID data, or we could pick up images or videos and transform this data in the actual, if you are, for instance, monitoring activities in a construction site. So our model is the evolution of the building, but also maybe the position of equipment, of the worker force. So this data should be transformed, and in the end, I want to know exactly what is the stage of my building, the construction of my building. And the G's, it would be aligned with, I want to make a report, I want to maybe control a semi-automatic machine, I don't know. I want to develop a plan. So this plan could be sent to a drone or a set of drones, and those drones, based on this plan, will get more information about one activity that was not properly looked at or in detail. So I could make this analysis to make a better monitoring system for me. And looking at specifically at the digital twin for a construction site, that is the subject of my collaboration with the GTEC group and their research. I think we could look at some design choices for our digital twins. And I pick up some opposing alternatives in each of these blue boxes. If we want to monitor our construction site, we could opt to modify the construction, the site itself. So we could put cameras in parts of our environment, or we could modify the materials, equipment, or workforce. So I put a device in the helmet of the worker. I put a sensor in a machine. So it's different forms, so you could gather real data from the real environment. But also, we could choose for each activity a different hardware and software, or I could use cameras and images. It doesn't matter if the camera is inside a drone or a robot dog or fixed in our construction site, but images allow us to make really different and general processing, so we could extract a lot of different information. It's more flexible. Also, one alternative is that we use extensive cloud computing, is services that we pay and are on the cloud. It allows us to develop fast, but also we need to consider that when you send sensitive information to the cloud, you lost maybe data confidentiality. We depend on third parties, so sometimes it's better to bring all these things to the edge, to the field, and we have all in our computers, in our network. And the last design choice that I brought here today is look at, maybe we could look at the micro scale of what is happening on the construction site, but we could also look at the macro scale and consider not only one site, but the many construction sites of a construction company. And our digital twin could represent, I think, different, more general, and maybe brought more value instantly to the construction company. I provide here an instantiation based on the GTEC many researches here. So we could see the some possible apps that uses images from a drone. Each one will provide or look at different components to update our digital twin. We could look for protection equipment, personal or collective. We could also to look at quality or pathologies in the building being constructing. The processing could be use YOLO to extract those informations, but it should also provide a way so we could geo-reference this information and add to the status of our model in that part of our construction site or building that is this problem that the manager should be aware. We could extract the information for the digital twin to provide a use that could involve other technologies as blockchains. And we could create some Gs that are merely dashboards of information or reports. So bringing out all what we have been talking in this lecture could provide a digital twin of the construction site. Somehow, as we look at this diagram or this framework instantiated. And also we could in the same or for the same building use a specific kind of sensor, RFID, and we could look at the sequence of production, when it starts, when it ends, each activity, and it could also help understand if we are far ahead our schedule or getting behind it. And based on what is happening, we could give the managers more information so it could make a decision to increase the workforce or have other decisions. And to finish, in this framework, when we should decide what would be our Fs, what would be our Gs, I think it's interesting that we will be using a lot of different capabilities, and some of those capabilities could depend of artificial intelligence or other programming functions. Probably we will need to make data integration, real-time processing, batch processing. And I like this. This is provided by Digital Twin Consortium. And I think they made a fair list of capabilities that we could or should use in Digital Twin. So depending on the F that you are developing, you should consider what capabilities that F should provide, and based on that, you hire or develop yourself these capabilities. So in conclusion, what we saw today, one digital twin should mean the integration of different models. You need to consider the geometry, you need to consider the SISEX, the behavior, and maybe some rule model. It has a data-driven nature. When you use simulation data, real-time data fusion between physical and virtual, and beyond the historical data, we have also the statics physics data. The physical and virtual spaces are connected. In that way, the physical entities could be better controlled, and the virtual model could be progressively optimized and upgraded. And I also think the maintenance will be a major contribution area for the digital twins. So that's it. Any questions? Thank you.